Welcome. So I know the talk was advertised as a German talk, but I was asked if I could do this in English as well. So is anyone strictly against hearing this talk in English? Please raise your hand and throw popcorn at me. Oh, no popcorn? Great. Thank you very much. So welcome. We're going to talk about containers and data applications on the same cluster in the next 45 minutes. If you have questions, use the app or like catch me when I'm around. So we have quite a packed schedule for the next 45 minutes. And the actual title of the talk is Having Fun with Monkey Islands. So we will shepherd our real topic with some fun because we're in the cinema, having popcorn, all that stuff. So enjoy. My name is Johannes. I'm working for the company Mesosphere, which has an office here in Hamburg. And you can find me on the internet. So if you have further questions and you can't find me today, ping me on Twitter, and we have a chat on our DCS community, our website. My name is Unterstein at Mesosphere. So ping me and ask me everything you wanna ask. Okay. Well, let's give you a short summary of our recent service architectural change. So at the beginning, we had a monolith, right? So at the very, very beginning, we built software running on one server, on one desktop application. So we had hardware, like these notebooks, and an operating system, Linux, Windows, Mac, whatever, and your application on top. So this was quite easy, right? The next evolution was we built web applications. We got remote users. So it was kind of different. So we needed to handle more requests at the same time. So it was more challenging. And then we tried to use the same applications but scale out, so to add more services to get a higher availability and to balance our loads on each application and on each server. But soon we recognized that building those big applications and just replicating sessions or load balancing sessions is probably not the one silver bullet. So we separated our applications. So we split it up between web application and a service layer. We call this service-oriented architecture. It was quite a hype a few years ago, but it had some very nice thoughts about it. So we wanted to separate concerns. We wanted to separate different applications to have their own semantics and their own reasons, like UI and a more service layer. And so we could also move faster. So we could separate the teams, and we could like split the UI handling, like the UI logic from the business logic, and make clear cut and clear API between those applications. So it was quite nice. And then we thought, okay, so we're at the point where this is really scaling great, but I don't want to have an operator going to my data center every time I recognize that my user base is growing. So we started introducing an infrastructure layer to be able to visualize all the machines, all the boxes, and to be able to automate this and add those servers automatically. But then we get a bunch of downsides. So we were able to provision faster to add some more servers in a shorter period of time. But we also make sure that this is working, that we have a proper configuration management for these servers, and we need to automate all that stuff. And then we thought, well, this is quite nice. We can add servers all the time. It's super easy. So why not splitting our application development teams even more and making stuff that call microservices? So we have a ton of services, each serving exactly one purpose, and having be able to do real polyglot development, like having teams serving one application and their freedom of choice what their technology is. And when you run multiple servers on one machine, you get a better resource utilization. So if you're running one Java application on one server, you probably waste a lot of CPU and memory because this one process is not able to utilize the entire machine. But when you split this between multiple applications, you probably be able to get a higher load on your hardware or on your virtual hardware. Okay, so great. But then a hype named Docker came up. So we started to run everything in, not in Grok, in containers. And the nice thing about Docker and container was that you were able to pack all your dependencies in one tarball, basically, and just ship it. And you'll be able that your Java application has all the dependencies it needed to operate, and you were able to transfer it, right? To load it to a private registry or Docker Hub, and then others could just download it and start it. So this whole setting up of servers was gone because you had this nice infrastructure. So your image basically now looks like this. So you have a container runtime between your applications and your operation system. But when we're talking about like containers in production, so we're not done by adding this red box in the middle of our architecture. So we need to talk about like how to really having an automation in there. And when we talk about production, we need to talk about scheduling, like container scheduling. We may think about where to place our containers. So imagine you have 20 servers, and you need to have a strategy where to start your containers. Maybe you have placement constraints, like only start one container of one kind on one box, or how to handle scalings. So if you want to scale up from 1 to 20 instances from one application, it's probably a bad idea to schedule all the containers to one host. So you need to think about those constraints. And you need to talk about resource management. So you need to limit your containers in the resource consumption. So in this example is really bad. So this container consumes all the resource of the host, and you didn't have any benefit from using containers. And the last point, you need to think about service management. Like all your containers need to travel to the same direction. So their containers need to find each other's. Maybe you have dependencies from one container to another, so you have some restrictions. And when we're talking about these three topics, we're talking about container orchestration. And as much as I love containers and ships, we're talking about these things. So as I teased a little bit, on the scheduling hand, we need to talk about placement, so where to start my containers, and if they fail, how to replace them. Like replace them on the same host or in a different host, maybe in a different data center. So who knows? It's depending on your requirements to your orchestrator. And how to handle upgrades and downgrades and scalings. Like these are interesting topics for the first part of your orchestrator. And the second part is like resource limitations. We want to limit our processes to consume only a few CPU a percentage, or only a defined amount of memory, or GPUs. Like GPUs in the last year of GPU consumption is super popular to not only to mine bitcoins, but to do reasonable business stuff as well. And like other stuff like IPs and ports, so you want to limit your containers to consume only dedicated ports and stuff like this. And the last part, we need to talk about like load balancing and service management and how to find each other, and maybe you have dependencies and stuff like this. So when we go back to our first image, it probably looks like this, so it's really scary right now. So you have your infrastructure, same as in the old days, then your machine or operating system, then you have your container runtime, and then all this stuff we recently talked about, and then comes your web applications. So we need to have a automated stuff in the middle now. And you was not alone. So like this was a short teaser of how our service architecture moved. In the meantime, we had MapReduce crunching data, and NoSQL and fast data technologies are also being really popular. So if you look at more modern kind of architectures for serving really big amount of data and doing real-time analysis on top of this, this is a quite popular architecture. So imagine like an example of a bank. So you want to have a bunch of devices, you have ATMs, you have mobile payments, you have maybe your phone and you pay by credit card or stuff like this. So you have a bunch of sensors sending events to a dedicated backend. And the first step is to ingest those events. Like you need to queue up all the events and store them for a certain amount of time to be able to be flexible to several load peaks. And then you need a store to persist these high amount of data. And afterwards, after you stored your data, they are more unstructured and not really processed at this point. you want to analyze those data and maybe make smart business decisions on top of this. Maybe you want to do real-time analysis if the user is currently trying to use the credit card, is going to be a fraud people, so is going to like fault you and using a fake credit card or a stolen credit card, stuff like this. You want to be able to make real-time decisions based off a really big data pool. And on top of this, you want to like have some nice visualization on top and an application who does this business decision and propagate it to the other stacks. So this kind of stack, I placed some Apache projects as examples for those kind of parts. I mean, now going from the right-hand side to the left-hand side and having a look on all those tools. So beginning with analyze. So I put Apache Spark. Apache Spark is quite a big representative for the stream processing area. But you could also use like Flink or Apache Storm or Apex, also a great project for doing a real-time streaming, in-memory streaming. And you can separate these frameworks by this micro-batching kind of thing. It's quite unique for the Spark world. So you have a batch of small sequences in each operation. Or native streaming like Flink or Storm would do, like one operation on each element in your stream. And when you then go to the store area, so like streaming is quite only a few representatives, but when thinking about stores, you have a huge amount of choice currently. You can choose your store based on your dedicated needs, so you're not limited to SQL anymore. So not limited to a structured storage. You can store in the format your application needs to consume. And again, you can order them. For a different use case, you can use a different store. You can have relational databases or key value stores if your application needs those stores. Or you can have a graph database or even hybrids, document stores, time series stores, and plain file stores. So currently, we have a great choice of technologies to solve our issues. And now I want to show you how great it would be if we could operate all those fancy technologies together on one cluster. But let's go one step back. So before I joined Mesosphere, I was doing project business for the European enterprise market. And what I often saw was you have a project, you can have 30 nodes, 50 nodes, 100 nodes, whatever. But what would you then typically do? You would divide your cluster statically by application. So let's say, in this example, we get 30 nodes, reserve 5 for Flink, 5 for Cassandra, maybe 10 for our microservice architecture, and 5 for Spark. So the numbers are quite odd, but okay. So you pin one application to one node to serve this application. But this has a bunch of disadvantages. So for example, when you're having an online shop and you're in the main selling hour of the day and your microservices are super busy, maybe 20% drops. So you have only 80% of your cluster left. And on the other hand, Flink or Hadoop is idling, and this part of the cluster you're paying for, or you paid if you do on-premise, is idling and not able to shift dynamically to cover those failures. It's quite bad. And on the other hand side, you need to optimize each subpart of your cluster against load peaks. So you need to hold the resources, CPU, memory, and disk and IPs, and whatever you need to run your operation to be able to survive load peaks. And maybe you have application which has different load peaks over the day. So in this example, Hadoop, Spark, and your microservices are running load peaks at totally different times of the day. So it would be really nice to share the resources between all applications based on their load peaks on one cluster. So on the other hand, if you have this picture, you have on the left-hand side your dedicated static partition cluster. And what I saw and what we see as Mesosphere is that you have an average of 10 to 20% of CPU usage on an average cluster in the industry currently. But if you would be able to dynamically shift all your applications around and virtualize them and run them in containers, you would be able to like serve all your production with less nodes, but a higher utilization. And this is the point where Apache Mesos comes into the game. So Apache Mesos was invented at UC Berkeley. There were 3 students doing their PhD thesis, and they wrote a paper about fine-grained resource sharing in a cluster between different applications. So basically, exactly the problem I was talking about. And at the same time, Twitter had these crazy scaling issues. So Twitter had more new users that they could carry service to the data centers. And by accident, one of these students knows someone at Twitter, and he gave a tech talk there. Twitter was super interested and really pushed the source code development forward. And in the same year, they published a source code draft of MESOS. It's implementation of those paper. And it enters Apache Incubator. And then by accident, they know someone in Airbnb, and they introduced it there. And they thought, oh, geez, this is crazy. You have so nice scaling effects. We need to share it to the world. And then they started project business around Mesos, started to develop DCS. So that's what I'm going to show you in a minute. And carried all the best practices from the project business into a product. And what they did from 2014 to 2016, they open sourced all this stuff. So everything I show you today is totally open source. You can install it on Amazon, on Azure, in your own data center. Totally up to you. You can download it, try it for free. It's open source. Okay, but let's go back to Mesos. Mesos is quite popular nowadays. So Twitter runs their entire production on Apache Mesos. And they so they published their numbers. This was about 28,000 nodes to serve twitter.com. And also Airbnb runs Mesos, and Netflix and Siri. So Apple runs Siri on Mesos. It's roughly the same cluster size. And imagine what they are possible with this. So imagine you have one Siri application for each language, targeted to the audience in that country, speaking their language, handling their specific like applications. So yes, they're calling Uber. Maybe in Hamburg they're calling My Taxi and stuff like this. And you'll be able to scale up your installation based if your user base in Germany is awake or not, or if it's in US awake or not, if it's UK awake or not. So you're able to use one cluster and scale up your applications based on the load peak of your application, and scale it down if your user base is asleep. So this is Apache Mesos. And Apache Mesos is, under the hood, contains basically 2 parts, like a master node holding a state about the cluster. And the master node is only about managing the resources. And then the agent's on the other side. And the agent carries resources. An agent has CPU, memory, disk, IPs, and stuff like this. And the agent shares those resources to the cluster. So the agent would say to the master, hey master, I have 3 resources. Please share these resources with all the registered schedulers. And on the other side, we have schedulers. We have Marathon, which is our kind of interpretation of a container orchestrator. But you can have more schedulers on top of Mesos. So you could have Myriad, it's a bridge for Hadoop. You could have a Cassandra scheduler, Kafka scheduler, Cassandra scheduler, and way more schedulers are currently implemented. So we have kind of 2-level scheduling. So Mesos by itself is only doing resource sharing and distributing the resource offers fairly between all registered schedulers. And the schedulers itself, they can be implemented in C++, in Java, in JavaScript, whatever you want to. They just need to speak a HTTP API. They are doing the business decisions where to schedule which task. And this is quite good, because scheduling microservices, those stateless applications, are super different from scheduling Cassandra or Kafka. So when you're scheduling a Cassandra node, you probably want to wait a couple of minutes when your container is dropped. So you don't want to instantly replace your container somewhere else in the data center, because then you have a full data replication. And if your Cassandra cluster is quite big, this is super expensive. So maybe you just have a network partition and your agent is disconnected by network, don't know. So you want to wait a couple of minutes so Cassandra can handle disconnected nodes very well. So you want to wait a couple of minutes to see if this would come back or not. And you can't do this with a generic overall scheduler. This is why you have this kind of two-level scheduling. But when we're now talking about like databases or Spark and streaming stuff, we need to talk a little bit about storage. So we heard in the first talk today a little bit about storage, and that he would not advise you to run your database on top of Kubernetes. Maybe this is right. But in Mesos, you have like storage as first-class citizen. So what you basically have in kernel applications, you have three kinds of applications. So you have stateless applications, like in a Java application and in Nginx and stuff like this. They're producing logs, sure, but we'll have solutions for handling logs. But they don't hold business-relevant data because they're not data stores. And you have scale-up databases, like traditional SQL databases. These kind of applications scale by adding more CPU, more memory. And you have scale-out databases, like databases written for distributed systems, like Cassandra, MongoDB, Elasticsearch, database like this. And for these kind of applications, Mesos offers different storage options. So for stateless applications, you get a default sandbox. You get a change root to some folder in the box, but when your container dies, Mesos will take care that these temporary folders are deleted after a configurable amount of time. If you're using scale-up databases and you're not using cluster versions of MySQL, for example, you're doing backups, everything is fine, but when one container drops, when one SQL instance is failing and you don't have a cluster, you're probably in a really bad situation. And you could use external storage for this, so that you have your SQL data store on an external network storage. And when the container drops, you can just restart a database container somewhere else in your cluster, but connect to the same distributed file store, so your data is safe. But now, a really huge amount of users are using these kind of scale-out databases. And these databases have inbuilt replication. So when you add an Elasticsearch node to a cluster, this node will take care to replicate all the needed data and to join the cluster fully. And if one node drops, Elasticsearch will take care that all the data is also fully replicated with the left nodes. So you don't need replication on network file system layer. You have already replication. So these network writes are super expensive. You don't want to have them. So what we offer with persistent volumes is you get a label on the local disk, so full performance on writes. But when container is exited because of a failure or because of maintenance, so you want to do an upgrade of your Elasticsearch node, this data is stored and you are able to reschedule the replacement task on exactly the same data again. And then the database can decide if it wants to like only replicate the last 2 minutes or replicate, like do a full replication. So this is quite unique, these persistent volumes in the Mesos world. Okay, so now we have everything together to talk about DCS. So we talked a little bit about DCS. So DCS is basically everything I just explained to you. So you have Marathon to run your containers, and you'll be able to add more schedulers to your cluster to consume resources, to do streaming, batch processing, machine learning, key value stores, or time series data stores, and all that stuff. You can run all this on the exactly same cluster, and everything is running on Apache Mesos. And we added a bunch of, we added a nice UI and a nice CLI. I will show you this in a second. And a ton of security concepts, load balancer, service discovery mechanisms, and all that kind of stuff. Okay. And the great thing is everything is open source. We added a bunch of features, and we have a really nice and shiny website. So if we go to dcs.io, I'll make it a little bit bigger for you. We have a huge documentation and demo section. So if you want to install it on your own and toy a little bit, you could do the demo I'm going to show you in a second, or do one of our predefined demos to get used to DCS. But the installation part is quite interesting. So you have 3 options. You can install this on your box, Sure, you can't run a proper Cassandra cluster on a notebook, but you can install some starter applications, and this is done via Vagrant. So you have like one command to install everything on your box, all the 30 open source projects which contained in DCS on your box. You could install this on premise in your own data center, if you want to, behind your own firewalls. Or you could go to a cloud provider. So we offer templates for Google, Amazon, and Azure. And if you go to Amazon, so this is super easy. So just pick your region, like Ireland, and decide if you want to have a high availability DCS cluster, a regular one, and hit the button. And it takes, I think, 15 minutes to boot up. But then you're good to go. And I did this for you this morning. I think this is quite the biggest UI we ever showed of this application. And when you successfully logged in to your cluster, you see this. This is an aggregated view of your cluster resources. So you see in your cluster you have 30 CPUs, around 100 GB of memory, a little bit of disk assigned, and you get an overview of your service health. So you see how many tasks are healthy. So when you're running productions, you want to make health checks. Health checks is a ping to your application to a configured endpoint to see if your application is going well. And you see here if your containers or data services are going well or if you need to interact. And you see how many tasks are running and how healthy DCS is. And the detail that we're dealing with a cluster containing 7 agents is just a detail. And honestly, I don't care about how many agents my cluster has, as long as all my applications are running and my business is going. So you probably only care about this number if you have here a really high amount of utilization or a bunch of unhealthy tasks. Okay, but let's go the left navigation from top to bottom. Everything you see behind the service tab is marathon, so container orchestration. So you can run a service, start a container, and you can decide between single container or multi-container, like co-located container as Kubernetes does. And you can say, we want to start the application. You need to give the application name, let's call it Sleeper, and define that you want to have 0.1 CPU, 100 megabyte of memory, and you want to run the bash command sleep 100. And then you can decide if you want to run a Docker container. So then you need to specify a proper Docker image name, or if you want to use the MESOS runtime. So MESOS was invented 2009, and one of their first features was to implement resource isolators, like basically the same things Docker does, like C groups, namespaces, and change roots. So if you're using MESOS runtime, you can run this bash command, and MESOS will wrap around on the fly container, making sure that you have a change root to your sandbox and an isolator to only to limit your CPU consumption. Okay, let's do this. Let's start a sleepy task on one of our 7 agents. And this is starting quite fast. So we're just going to MESOS agent and say, hey, please start this. And the nice thing is we can scale this really easily via the UI. I can say scale to 10, doing a distributed sleep. And then MESOS will pick 10 agents to start those 10 sleepy applications. And if you want to treat your applications more like pets, you can inspect those and see the real nodes running this. And if you have port exposed, you can inspect this, see the logs, see the files on the sandbox and stuff like this. So what is behind here is, as a JSON configuration. So as a JSON configuration posting to Marathon describing my application. You can also place placement constraints there, like start the sleepy task only on these nodes, or start only one sleepy task on one node, or spread my applications evenly. So if you have 7 nodes, you want to have all nodes running one application of the sleepy and 3 nodes running 2, and don't have all the 10 on the first node. So you can all configure this here. Okay, So let's go down the navigation. You can have all the things I just showed you as a scheduled container. So if you want to run a cleanup container every night at 3 a.m., or you want to do some analytics every night at 4 a.m., you can do this and run just a bash command or a Docker container every night at a defined time of the day. And we have the universe or catalog. So this is our kind of interpretation of an app store. So you can install a proper Cassandra cluster with just 2 clicks here, or a proper Kafka cluster with just 2 clicks, or Spark, or Elasticsearch, or you can even run Marathon on top of Marathon if you want to. But I want to install now Marathon LB. So Marathon LB is quite interesting. It's a load balancer, an HA proxy, and this load balancer automatically configures itself by the running applications in Marathon. So we will see this in a minute. And I want to install Zeppelin. Zeppelin is a web UI, and it basically only has 1 or 3 big text areas, and I can put Scala code inside. And when I hit the deploy button, this Scala code is compiled to bytecode, and then this bytecode runs on a proper Spark cluster. So I can do in-memory map reduce on a real cluster of 7 nodes just by pressing 2 clicks to install it, go to the website and hitting the run button. So this is super nice. Okay, but now I installed Marathon LB in my cluster and Zeppelin. It's currently deployed, it takes a while. So now I want to show you our actual application. And our actual application is, I want to serve jokes via HTTP REST endpoints. And for this reason, I have a database, I have a SQL database, and I have a Java web service. And you can run this locally, start your Java service on your box, and start your SQL database on the box and connect it. But in this demo, I want to use Docker Compose. Docker Compose, make this a little bit bigger. Docker Compose is a tool to start multiple Docker containers at the same time together and bundle them together. And I'm doing Docker Compose up. And at the same time, I'm showing you the Docker Compose YAML file. So this is basically containing the database. The database is a plain MySQL database, and I added all the jokes to the database. And I did some configuration for the username and the password, but nothing special in there. And the other one is a Spring Boot application. And it has this Docker image name I want to export, the port 8080. This container should depend on the database, so it should start when the database container is started. But now I want to start the exactly same containers on my local box and on Docker Compose and later on DCOS. So I need to configure my containers based on environment variables because they're super easy to inject to all containers. So now I'm saying I will have my Spring data source URI to the database container, my SQL port, the user is Chuck, and the password is Norris. So we're doing Chuck Norris jokes. So for the next remaining 10 minutes, please ignore the political activities of Mr. Norris and just stick to the funny old days. Yeah, so now we're going to see what we get from this application. So this application only has 2 endpoints, basically 3 endpoints, like / on root, and you get this. You get a random joke out of the database. In the last line, you get a version. I also configured this via environment variables. You get some details about what language you're querying. Each instance get a UUID, so when we're later scaling it up to 20 or 50 or 100 instances, I want to show you that I have real load balanced responses. And the host address which are responding. So I'm currently using Docker Compose. So this is a bridge IP network. So this is super easy, right? Okay. And now we saw Docker Compose. But Docker Compose, so if I do Control-C, it stops. It's not that nice. I have the same configuration for my application serving Chuck Norris jokes for Marathon. And I'm now using the CLI to install it to my cluster. I'm doing DCOS Marathon group because I want to add a group of applications. Add marathon configuration in a specific version. And then I get a deployment ID back. And when I now go to my DCOS dashboard, I see that here's a group chuck jokes. And I have a database container and a service container. And I'm currently installing 2 services and 1 database. So let's have a look about this configuration. Now, this configuration is a little bit more verbose, but I can also configure more things there. So as you saw, we have a group, like the chuck jokes group. And we have a database container. The database container has resource limitations, 1 CPU, 1 GB of memory, 1 instance. And I want to use Docker. And I want to use the same Docker container as I used for Docker Compose, like exactly the same container. To be sure, when you're running from local testing to stage to prod, that you're running the same things. So this is super important. But now, here I don't have Docker special network features. So we need to define our networking service discovery things. So in this example, we have a random host port, but we say that we want to have the container port 3306, so the MySQL port. And then I added some labels for service discovery mechanisms. So I want to export the hostname port combination, that the hostname port combination database and MySQL port is always mapped to this container. So then I can say, I want to have database 3306 and everything is mapped to this container on this port. Or additionally, I could use IP pattern service discovery, saying that the virtual IP 3.3.0.6 on port 3306 is also load balanced and always rewritten to this container. So I said it's load balanced, but it's a MySQL database, so it wouldn't work with this. But anyways. Okay, so the next configuration here would be a health check. So a health check in Marathon is, please use the TCP protocol and give it a grace period. So give it an amount of time to boot up and not doing health checks during this period. And doing an interval, so doing every 60 seconds a ping over TCP to this port 3306 and see if it's open. If it's not open, you have a max consecutive failure rate. So if it fails 3 times in a row, this health check, Marathon will make sure to start a replacement. And if this replacement is healthy, stop the wrong one. So we're seeing this in a second. Okay, this is our database. Now go to a Java service. So I have the service. It depends on the database. We also have CPU, memory, and instance configuration. We also have a health check. Now we're doing HTTP health checks. And I do have a toggle. It's a Java Boolean. And if I do a delete on this URI, this toggle will flip from healthy to unhealthy. So I want to show you what happens if something goes wrong. And now we have max consecutive failures to 10 and an interval of 2. So if one application is not running good, it will be replaced after 20 seconds. And here the same, I'm running the same Docker container, exporting port 8080, and now I'm configuring the database to database dot some magic suffix, and I'm good to go. And the same as I would do in Docker Compose. But now we have service version 3. Okay. Then I have some upgrade strategy and some magic configuration for our load balancer to get there externally, but we will see this soon. So now I talked enough that the application is successfully deployed. So we have one database and one service, and we now can go to this URI and configure it as external URI for the load balancer. And now this is running on AWS. So I get the same responses from the same image, but running somewhere else. And now you can see that it's load balanced. So if you look now, you can't see it. So maybe let's scale it a little bit. Marathon app update. Now I need to do chuck jokes on service. Oops. And I want to update the instances property to 20. So what now happens, I get the deployment and I want to rescale my applications from 2 to 20. So now I trigger the deployment and my target state is 20. So what we saw, we have 2 healthy applications and 18 running application, so the Docker container already started, but the servlet container from my Spring Boot application is not yet responding to the health checks properly. So now we have more green dots here. Okay, everything is running. So when we now go to our external load balancer, you can look to the host address, and you see that you really have a load balanced response to your application. So now 20 Java services responding to my GET requests. Okay, great. So now we installed our application. We can inspect all these fancy Spring Boot logs if we want to. We installed it, we scaled it. Now let's break it. Okay, so we get this URL, and we do a curl -delete on the health endpoint. So maybe like break 3 applications. So it's now happening. Oh, there, 1, 2, 3 red dots. The first step when an application is marked as unhealthy, the load balancer will not route traffic to these unhealthy applications to reduce pressure on it. That's the first step. But when we then pass 10 failures in a row, so we see it here currently, this is the newly running application, updated 1 second ago, Marathon would assume that this application is so unhealthy that it will never come back and be healthy again. So Marathon will start new applications to replace the unhealthy ones. Okay, great. Now everything is running. So I could do now a rolling upgrade from version 3 to version 4. So the default is rolling. I have 4 minutes left, so we're super in time. So we can do this. Every serious change would trigger a deployment, and the default is a rolling upgrade. So we now go from service version 3 to 4, or maybe Docker image version 1 to 2, it's exactly the same. Marathon will do a rolling upgrade. A rolling upgrade means, and I configured this, that you would start in my configuration 15% more instances than I configured. So 20 instances would be 3 new ones, and then stop 3 old ones. So you have a real rolling upgrade. So we have a bunch of healthy new ones. So when we now go to our application, have a look at service version 3. So now we have an answering 4 version, so a new one, and an old one. And when I do a refresh again, we get a 4. So every time you want to have a 0 downtime deployment, you need to make sure your applications can handle the same database scheme in 2 versions. And if you do rolling upgrades, it's really important because you really have 2 operating services on the same time, 2 versions. But we also offer support for green-blue deployments, like the classic one, start everything on top again, and then do the hard switch, or do more modern canary upgrades where you start maybe 1 or 2 new versions and route like 5 to 10% of new traffic. And if you gain trust in your application, like start the rolling deployment to get 100% new applications. You can do everything with DCRs. Okay, great. So now we started, scaled, braked, and updated things. So now let's have a look at this data analysis part. So I installed Zeppelin. So this is really great. So you have a web UI, and the important things for demos is you can upload predefined dashboards. I do this for you. So we have the Chuck Norris analysis. I promise this will be super funny in the end. So every Zeppelin dashboard contains 3 steps: loading dependencies, doing analysis, and displaying the result. And this is like plain text Scala code I put in there. So excuse me that I choose Java to do this. I will explain everything as good as I can. So this is plain text. I put the run button, and now this gets compiled. This is the first step. So this takes a while, so go to the second one. So here, the first step is create a connection. Now I'm using this kind of IP pattern VIP discovery mechanism. Again, with user Chuck and password Norris, everything the same. And then in this line, I would load all my data. I would go to the jokes table, selecting all English jokes, going from 1 to 5,000. So we have 4,500 Chuck Norris jokes. Do this 10 processes in parallel, and you're only interested in the jokes column of your application. And then you would get a sequence of jokes. And then we're doing a word count. So lesson 1 in MapReduce, a word count. So we have a list of jokes, list of sentences. And with these lines, I'm transferring a list of sentences first to a list of words. So I'm splitting by white space. So then one sentence is a list of words. And then I'm combining all those words together and stripping special characters, I'm not interested. And then having one huge list of words with all jokes after the others. And then I'm filtering every joke, not having a small size. And then I'm doing the map step in our MapReduce. So I'm mapping each word to a tuple of word and one. So I'm transferring the word chuck in chuck and one tuple. And then I'm reducing by key. So reducing by key means if I get the same key, chuck, I'm doing transform from chuck and one to chuck and two. And I can do this highly in parallel because they're idempotent operations. Then I'm storing this to a temporary table, and this is my job. So, and this takes a while, we don't have so much time, but the result is prepared already. So the result you can query by SQL-like language. And who would thought in our jokes we have 4,500 occurrences of the word chuck. Wow. And then a little bit less occurrences of Norris, and then we have some filling words with that when one's roundhouse. Okay, great. So we have 220 occurrences of roundhouse. Okay, but I want to show you one thing. So this is super funny. Only you just have they doesn't have kick. 160 occurrences of kick, and the next thing is 150 occurrences of face. So maybe this is correlated. So if I would be a data analyst, I would dive into this kind of thing and would see if this is really correlated. Okay, now we have everything together. We saw microservices, or at least we saw one service, to be honest. But you could imagine that you can do a bunch of things there. And we saw that we can combine this with data applications. So if we go, if we go back to our DCOS dashboard, we can see that this is super utilized. So we use 90% of our CPU shares and 30% of our memories. So this is super awesome because we're just using one cluster to operate everything. Okay, great. So I'm done with the technical part. I want to say thank you, LucasArts, for Monkey Island. This was a great game. Thank you very much. And thank you for the funny images. This presentation wouldn't be possible without these. And yeah, no presentation without a three-headed monkey. Thank you very much.